Let's do the mathematics so you'll better understand the acceptance-rejection method. I'm going to use a triangular distribution as my target PDF, so we're trying to obtain a random number from a triangular distribution. Triangular distributions can be solved using the inverse transform method, but I'm going to use it because it's a nice easy one to show the mathematics. So we've got some probability distribution, which goes from, say, 20 to, say, 30. And it's a triangle with a peak at 25. This is my probability distribution. Now, I need a majorizing function, so I'm going to pick a nice easy one, a uniform distribution. So what's going to happen is we're going to keep anything that ends up in here and throw away anything that ends up out there. Now, unfortunately, because the triangle is half the size of the rectangle, we're going to throw away half of our numbers. That's the problem with this method. You throw away many of your numbers. Let's go to our table to find our first number. The first number is 94737. So we take this number and divide it by 100,000 and we get U1 equals 0.94737. Okay, now we need to have a number between 20 and 30. So if this blue thing is my f of x, what is my capital F of x? My capital F of x looks like this. So what's the equation of this line? We need to work out the inverse of it, which actually looks like this. Now, what's the equation of this line? Y equals mx plus b. The slope is equal to delta y divided by delta x. So my delta y is 10, my delta x is 1, giving a slope of 10. The y-intercept is 20. So y equals mx plus b gives y equals 10x plus 20. So the random number that we want will be 10 times u plus 20. So therefore, x1 equals 10 times 0.94737 plus 20, which equals 29.4737. So we've got a point that's somewhere right about here. So now we take our next number, which is 87259. So we need to know what is this distance divided by this distance. The first question is, what is this value here? Well, in order to do that, we need to know that this triangle has a base that's 10 wide, and the area of the triangle is 1. We know the area of the triangle is 1 because it's a probability distribution, and so the area is 1 by definition. So therefore, if it's 10 wide and the area equals 1, we're saying that half base times height equals 1. Now the length of the base is equal to 10, so the height equals 0.2. So this line goes from 25, 0.2 down to 30, 0. Once again, the equation of the line is y equals mx plus b. The slope m is delta y divided by delta x. Delta y is 0.2. X goes from 25 to 30, so delta x is negative 5. So m is equal to 0.2 divided by negative 5, which equals 0.04. Y equals mx plus b, and we know that the point 30, 0 lies on the line. Therefore, 0 equals 0.04 times 30 plus b, which gives b equals 1.2. So we get f of x equals minus 0.04 x plus 1.2. Now we look for our next number. That was the 87259. Substitute 29.4737 into the equation of our line, and we get f of x equals 0.04 times 29.4737 plus 1.2 equals 0.02105. So this height here is equal to 0.02105. What is the bigger height? It's 0.2. So therefore, f of x divided by g of x is equal to 0.02105 divided by 0.2, which equals 0.0526. Now, our second random number value is 0.87259, which is larger than f of x on g of x. That means we're up in this area, so we reject 29.4737 as our answer. So we need to start again. The next number on the list is 63856. We insert this into our inverse of f equation. x1 equals 10 times 0.63856 plus 20, which equals 26.3856. Just in case that doesn't match, x equals 10 times 0.63856 plus 20, which equals 26.356. Substitute this into f of x, and we get minus 0.04 times 26.3856 plus 1.2 equals 0.144576. So f of x on g of x equals 0.144576 divided by 0.2, which equals 0.72288. Now, we look at our table again, and we see that the next random number in the table is 0.66612. 0.66612 is less than 0.72288. Therefore, we accept 26.3856. So we've worked out that for our triangle, 26.3856 is a valid random number, and so we use it. As you can see, we're going to throw out about half of the numbers when we have a triangle inside a rectangle. If your function inside the middle takes out a bigger proportion of the whole, then you'll throw away less numbers.